Concentration and colligative properties formulas. Let's start with the concentration. We have the mole fraction and percent concentration formulas. The first one is the mole fraction, which all the time the answer must be less than 1. Second is the mass concentration percentage, which you just like getting your score and what is the equivalent percentage of that score if you're taking tests. The same for the volume concentration as well. Okay, let's try. Let's have this example. A 60 gram sample of sugar, C12H22O11, and by the way, if it is a covalent compound, we call that as a non-electrolyte. Okay, keep that in mind. Sugar is mixed with water to form a solution with a total mass of 500 grams. So just imagine the sugar is mixed with water and then the entire mass of the solution is 500 grams. So that is already included, the 60 grams of sugar. What is the percent concentration by mass of the solution? Now, which of the three formulas should we use? Since we're talking about the percent concentration by mass, we're going to use the middle one. And how do we solve that? Of course, it is just a simple plug and then solve. Okay, we have already the mass of the solute. We have the mass of the solution, the entire solution. Plug that in and then do the math. 60 divided by 500 times 100%, and that is now your answer. You have 12% by mass of sugar in this solution. Okay, now let's have another example. Okay, this time it is now in reverse, but it says a solution is prepared by dissolving sugar, same thing, C12H22O11 in water. The total mass of the solution is 500 grams still. And the solution has a 12% sugar by mass. So what is the mass of the sugar used? This time, the unknown is the mass of the solute. So we will be using the same formula since we're talking about the mass. We're going to use this formula here, the middle one, and we're looking for the mass of the solute. But we are given the percent concentration by mass of the sugar in the solution. Is it hard? No. This is still a simple plugging the values and then solve. So since we already know the percent mass, which is this one, and we also know the mass of the solution, which is this one, the unknown mass of the solute will be derived by using those two given. So we're gonna put it like this. We have 12% as the percent concentration by mass equal to the mass of the solute, which we don't know yet, divided by the 500 grams of the solution times 100%. And how do we solve this? You just need to do the simple math operations. We need to isolate mass of the solute. Mass of the solute should be alone. So we need to get rid of 500 and 100% by multiplying 500 both sides. 500 will now be eliminated on the right side, which will be like this. Now we need to get rid of the 100% as well on the right side because we need the mass of the solute to be alone. Just like finding x, we need to make the x alone on one side of the equation. So just imagine this entire mass of the solute is the x. Okay, so we need to get rid of 100%. And the way to get rid of that is divide 100% both sides, and 100 will now be taken away, and 100% will now be on the left side, or just cross multiply. That's the same thing. And perform the mathematics. 12% times 500 divided by 100%. The percent symbol will now be cancelled, and we have 60 grams mass of the solute as the answer. So if you use your calculator, of course, it will show us the 60 grams mass of the solute. So that's another way to use this formula. Okay? And it's the same thing. If the mass of the solution is the unknown, the same process that you're going to do. As long as you make the unknown alone on one side, and you can now get the value of that unknown variable. Now let's have another problem. A 75 ml sample of ethanol, C2H5OH, a non-electrolyte still. It's a non-electrolyte. It means we cannot break this down if it is dissolved in water or any solvent, is mixed with water to produce a solution with a total volume of 300 ml. Okay, so what is the percent concentration by volume, this time not anymore by mass, by volume of the solution? Which of the formulas should we use? Of course, the last formula, this one. We're going to use the percent concentration by volume, and the same process will be used. Since we already have the volume of the solute, and we also have the volume of the solution, just plug it, and we're just going to solve it using math, simple math. So 75 is the volume of the solute, and 300 is the volume of the solution. 75 divided by 300 times 100%, that gives us 25% concentration of ethanol by volume in this solution. So that's the answer, 25%. Now, what if it's the other way around? The percent by volume is already given, and the volume of the solution is also given, but we need to find the volume of the solute instead. So this is given, this is also given, and we need to find the volume of the solute. The same process. You need to plug in the values and then find the unknown. Okay, so we have 25% as our percent concentration, 300 at the bottom, which is the volume of the solution. Volume of the solute is unknown, that's what we're going to find, and times 100%. So the same thing, we need to eliminate all the numbers on the same side of our unknown, which is the volume of the solute. We need to eliminate 300 first. So to eliminate 300, you can do cross multiplication or multiply both sides by 300 to eliminate 300 on the right side. So that's 25% times 300. And the 300 now is eliminated on the right side. Now we need to eliminate 100% by dividing 100% both sides. And we got this. Do your simple calculation using your calculator. Percentage is now cancelled. Don't press the percent in your calculator. Just cancel it out. Okay, so there's no need to put it in the calculator because it will ruin your solution. So just cancel that, and you just need to enter 25 times 300 divided by 100 in your calculator, and the answer is 75 ml of the volume of the solute. That's it. Okay, so now what if the problem is like this? 60 grams sample of sugar, C12H22O11, again non-electrolyte, is mixed with water to form a solution with a total mass of 500 grams. By the way, these formulas can be used even if the solute is an electrolyte, just like salt. NaCl is an electrolyte. This is just an example, okay? It doesn't mean that these formulas can only be used for non-electrolytes. No, it can be used for both non-electrolytes and electrolytes. Okay, now, which of the formulas should we use for this particular word problem? Since it is now looking for the percent of the solute. Oh, wait. Oh, my bad. This is not percent of the solute, but the mole fraction of the solute. Sorry, mole fraction of the solute. Okay, so we're looking for the mole fraction of the solute, and obviously we're going to use this formula here. So to use the formula mole fraction, of course, we don't need to multiply 100% at the end. So all we need to do is, of course, we need to acquire the moles of the component, which is, we're talking about the solute, the sugar. What is the equivalent moles of that 60 grams? And the total moles of all the components in our solution, which is including the water. So first, we need to acquire the moles of each of them, the sugar and also the water. Let's start with the sugar first. So N is, remember, the formula for moles is mass over the molar mass of the sugar. So the mass of the sugar and the molar mass of the sugar. The mass of the sugar is already given 60 grams, and we need to find the molar mass of that sugar. So the molar mass of the sugar is, you can just use the given periodic table, and if we add the masses of all of these elements, we'd come up and approximately 300, wait, oh, nothing changed, I'm sorry, 342.30. Wait, I think the question changed. Ignore this. We need to continue the mole fraction. So we have the 342.30 molar mass of this solute, and that is equivalent to 0.175 moles of sugar. So that is now the one that we're going to put on top. Now, the bottom, the denominator, it needs to have the moles of the sugar and also the moles of the water. So we don't have the moles of the water yet, but we know that the water is 440 grams. We need to change that into moles so that we add those two up, the 2 moles, and we put that in our denominator, because the denominator means total moles of all the components, the sugar and the water. So we need to add their moles. So to find the moles of the water, we have that already here, 440 grams of the water, and the approximate molar mass of water is 18.02 grams per mole. And solve this, we have 24.4 moles of no, water. Sorry, water. And to solve this, to get the mole fraction, all we need to do is change the component word into sugar, because we're looking for the mole fraction of the solute, which is the sugar. So we're gonna put the moles of the sugar on top, or on the denominator, and we need to add the moles of the two. So we have 0.175 plus 24.4 in the denominator, and we got the answer 0.0071 as the mole fraction of sugar. Okay, and that's it. Now let's go to colligative properties, but where we will be only focusing on the formulas of the boiling point elevation and the freezing point depression. Okay, remember, we have these two formulas. They have the same process, the same way of answering. The only thing that you need to add if we're talking about the freezing is the negative. Okay? Don't forget that. The process of how you solve them is the same, but the only thing you need to add in the formula, if we will now be talking about freezing, is negative. And that's it. Okay? And reminder, in getting the Van Hoff factor, if it is a non-electrolyte or covalent compound, non-metals, all of them are non-metals, then the I is always 1 most of the time. Okay, unless if we're talking about the special cases, but we will not include that. But for electrolytes or the ionic compounds, example NaCl, if we break NaCl, because it's a combination of a metal and non-metal, then we can break them apart into ions. We have Na and then Cl, 1 Na plus and 1 Cl minus. So we have 2 Is. For CaCl2, if we break them apart, we have Ca positive cation and 2 Cl minus. Don't worry about the number of the plus and the minus. As long as you know how many of the Ca is produced if we break them apart, and how many of the Cl is produced if we break them apart. So there are 2 Cls if we separate them. So that's why we have 1 and then 2 Cls, 3I. This one is the challenging one. Al2, and in parenthesis SO4, and then 3 outside. Now again, remember, if we encounter a anion, we call that anion, the second one. Al is the metal, which is the cation. If the anion is considered as group, we count it as one group. And if it is inside the parenthesis, whatever number outside the parenthesis, it means it is multiplied by that number. Okay, like for example, if we separate Al2 parenthesis SO4 close parenthesis 3, it becomes 2 over the Al, because there is 2 in Al, So there are 2Al3 plus, again, ignore that 3 plus, plus, by the way, I'm not saying that you need to completely ignore those 3 plus and the minuses. Those are only helpful if you combine the ions into a compound. That's why we come up with this entire thing. We crisscross their positive and the negatives. But again, for i's, ignore those numbers. All you need to do, the 3 plus and the 2 minus, ignore those, because all we need to count is how many of them once we break them apart. There are 2 ALs if we break them apart. And there are 3 group of SO4. Remember, SO4 is counted as 1, so there are 3 of them. So how many of the I's we have here? There are 2 ALs and 3 of the SO4, so it's total 5 I. And that's it. That's how you get the I. So I hope that that is not confusing for you. Okay, now we're done with the I's. How about the K? Those are constants. Okay, now keep in mind, if we're talking about water, water has the boiling point, which is these numbers, and freezing point that we already know. Boiling point of water, if we know the solvent in the problem, these two will already be answered if it is water. Okay, if it is water, we already know what is the boiling point of the solvent, water, 100 degrees Celsius. Oh, sorry, not included this one. It's just 100 degrees Celsius. And for the freezing point, it's 0 degrees Celsius. Okay, so that's the thing that you need to remember. If we're talking about water as the solvent, then we already know these two. Okay, now we will be able to know these two as well. I guess you need to memorize these. The K for the constant for the boiling is 0.512, and the constant for freezing is 1.86. Okay, so those are the approximation of the constants if we're talking about water. Of course, if it is a different solvent, it would be a different K. Okay, but if it is water, these are the constants that you need to remember and memorize. Okay, let's try answering this problem. What is the boiling point of the solution prepared by dissolving 50 grams of sodium chloride, NaCl, in 500 grams of pure water? Remember, we need to use this formula, but we need to write down our given first, and we need to know what are the given derived from this word problem. So we're looking for the new temperature, and this is talking about boiling point. It means we're using this. We're looking for the new. Remember, this is the new. This is the original. Okay? Keep that in mind. We're looking for the new boiling point because it's asking for what is the boiling point of the solution. It means it is now with the mix of the solute. So we're looking for the new temperature. So this one is what we're looking for. This is the unknown in the formula. So to answer this, we need to have this, 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 and this. We need to have those values to answer this. Remember, to solve a variable, the variable must be only the only one that is unknown, and the rest must be given. So let's start with the original temperature, boiling point of the solvent. We're talking about water. This is pure water. It means the original boiling point of that water is 100 degrees Celsius. So keep that in mind. The next, what is the I? Are we talking here electrolyte or non-electrolyte? NaCl. So NaCl is an electrolyte. It means we can break this apart and it becomes 2. So we have I equal to 2. How about Kb? Since we're talking about water, water has already its own constant K, which is 0.512. Again, why did we use 0.512, not 1.86? Because we're talking about the boiling. Okay, so this is the constant of the boiling. So we're gonna use that. Next, what else? The molality. M. Small letter M is molality, and we've already practiced this before. So you need to perform molality first before getting this answer. So molality is not here. We don't have the value of the molality, but we can answer the molality out from the given here in our word problem. So to get molality, remember molality is equal to moles of the solute divided by kilogram of the solvent. We have the mass of the solvent here, which is 500 grams, but that is in grams. We need to change that into kilograms. So that is now 0.5 kilogram. Okay, but we don't have the moles of the solute yet. So how do we find molality if we don't have the moles of the solute? Remember, to get the moles of the solute, we perform this. N means the moles, the mass of that solute divided by the molar mass of that solute. And the mass of the solute is 50 grams. The approximate molar mass of NaCl is 58.44. Of course, you need to solve that using periodic table. Find the mass of the Na and add the mass of the Cl. And this is now your answer, 58.44. Solve these two, and we got the moles with 0.86 moles. And what should we do with this? Of course, we put that on top of our molality. So we have 0.86 moles divided by 0.5 kilograms. And we now have our molality. And put that there in our given, and we can now find the new boiling point temperature. So use the formula. The new boiling point minus the original boiling point equal to I times K times the M. Put all the values. We have the new boiling point minus 100 because our original temperature, boiling point temperature is 100 degrees Celsius. I is 2, K is 0.512, and M is 0.86. Multiply these three. We got this. And what should we do with this? We transfer the minus 100 to the other side and it becomes plus 100. And our new temperature becomes 100.88064 degrees Celsius, or just 100.88 degrees Celsius. So the temperature increases because it's elevation. And remember, if we're gonna solve for the depression, freezing point depression, it will be lower than 0 degrees Celsius. Keep that in mind. Okay, erase this. There should not be that. Okay, now, what if the situation is like this? What is the boiling point elevation? This time, triangle TB, that's what we call the boiling point elevation. It means it is now the change of the boiling points of the salt solution, NaCl, mixed with water, if the boiling point of the solution is 105 degrees Celsius. So how do we solve this? How do we solve this triangle TB? Okay, there are two ways to solve this and get the value of this. It could be this, which is that one, or this and that one. So it depends on the situation, which of the variables are given. But here in our situation, which of the two formulas is easier to use? If we're going to use this, do we have the new temperature? Yes, we have the new temperature, 105 degrees Celsius, because it says the boiling point of the solution means the new boiling point. Question is, do we have the original boiling point? Yes. Why? Because we are still talking about water, and the original boiling point of water is 100 degrees Celsius. Is that's easier, right? That's easier to answer. And all we need to do is just subtract the two. 105 degrees Celsius minus 100 degrees Celsius. The answer is 5 degrees Celsius. And this is what we call as 500 degrees Celsius boiling point elevation. It means it increases 5 degrees Celsius. That's why we call it boiling point elevation. And of course, in freezing, it will be different. You'll be performing the same thing, but it will become freezing point depression. Okay, for the temperature over the new freezing point. Okay, now how about if all right. How about if we're going to use this? Now, the question is, do we have I? Yes, we can find I because we know the solute is NaCl and that is 2, right? So we have the value here 2. Now, do we have this Kb? Yes, because we're talking about water, it means that's the same Kb, 0.512. Now, how about M? No, we don't have M because the formula for M, but we cannot use M. We cannot use the formula molality to find M because we don't have the mass of the solute so that we can change that into moles and the mass of the solvent for the denominator. We don't have that here in our given, so it means we cannot use this formula because M needs those two to get the molality. So the only option is to use this because that's easier formula to use to get this answer. Okay, but if this one, if all of the three variables here are given, of course you can use this. But if one of them is not given and it's impossible for you to get one of them, then you cannot answer this without all three of them given. Okay, now let's have another example. All right, wait, is this the same thing? Oh yeah, that's the same thing, sorry. Okay, now how about this? We have this example. An aqueous solution is prepared by dissolving calcium chloride, this time our electrolyte, CaCl2, an electrolyte in water. That's our new solute, and we're still using water as our solvent. If the final boiling point or the new boiling point of the solution is measured 102.30 degrees Celsius, what is the molality of the solution? Now, you might be confused. Oh, it's asking for molality. Should we use the formula M equal to moles of solute over the kilogram or the mass of the solvent? Yes, if the mass of the solute or the moles of the solute is given in the problem, but it is not given. It means we're not going to use this formula for the molality, but there's another way to get molality because molality is also present in our formula here, right? So, meaning all we need to do is just use this formula because M, small letter m, is also present in that formula. It means we need to have these other given to be present. We need this, 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 and this to be all given so we can answer this. Okay, let's try. Do we have the value of the boiling point, the new boiling point? We have the new boiling point, which is this one. Do we have the value of the original boiling point? We're talking about water. We already know the original boiling point of water, so that is 100 degrees Celsius. Although it's not given there, but we know the boiling point of water, the original boiling point. So that's why we have that as given. Next, do we know I? How to get I? Again, we need to find the solute. The solute is CaCl2. And what is the number of I? It's 3. Right? Because if we separate CaCl2, there's one Ca and there are two Cl. So we have 3. Now, do we have Kb? Yes. Since it's boiling, we're going to use 0.512. And we can now find the M. That's it. That's how easy if we're looking for the other variables instead. Okay? So, we're going to plug in all the values, solve this, because we can now subtract this right away, right? Don't overthink, just solve this right away. 102.30 after you substitute all the values, subtract them, the answer is 2.30, and multiply these two as well. So oops, sorry. Sorry. Okay, that's already the answer. So we got 2.30 after we subtract these two, and if we multiply these two, we have 1.536. And don't forget the variable m. That's our molality missing value. Okay, now to get the value of m, we need to isolate m. We need to get rid of 1.536, and to do that, we divide 1.536 both sides. and that's already cancelled. 2.30 divided by 1.536, the answer is 1.497 molal. It means that is now the value of our M. Without using the original formula of the molality. It means we can actually find molality by just using this formula. Okay? As long as the variable is present in the formula, it means there's a way for us to solve also that variable using that same formula. And that's it. If you have questions, feel free to ask.